you for joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Hello everyone, and thank you for joining us today, and welcome to today's webinar from our Standards Activities Board series. In today's presentation, Introduction to Interfacing Cyber and Physical World Standards. My name is Scott Levine, and I'm the Membership Manager here for the IEEE Computer Society. Before we get started, I'd like to address some housekeeping items. This webinar is being recorded, and you can ask any questions in the Q&A box you see on your screen. The speakers will answer as many questions as possible. When submitting a question, please do your best to reference the slide your question refers to. The goal will be to allow for a quick question or two after each presenter, then we'll bring both Professor Yoon and Professor Kim back online for a larger Q&A at the end. You'll get a copy of the slides, and the recorded webinar will be emailed to you tomorrow. During today's webinar, you'll get an inside peek of the activities occurring in the Interfacing Cyber and Physical World Working Group. And by joining the community, you can be part of the discussion too. As part of this network, connect with professionals from all over the world and share your expertise within the field. Visit computer.org website to find ongoing calls for participation for the standard in all of our standard groups. More information will be shared with you after the webinar, and again, you can always learn more at computer.org. Circling back before we get started, we say this before all the start of our webinars, this presentation is our two speakers' opinion. This is by no means a formal position, explanation, or interpretation of IEEE. Circling back to today's webinar, the Interfacing Cyber and Physical World Working Group will introduce six of their current activities. Our first presenter today is Professor Hyun-Ro Yoon, who received a Bachelor's of Science in Computer and Electronic Engineering from Yonsei University in Seoul in 1987, a Master's of Science and Engineering in Electrical Engineering and Systems from the University of Michigan in 1989, and a PhD in Computer and Information Science from Syracuse in 1999. From 1999 to 2003, he was a principal researcher and a group leader in the Mobile Multimedia Research Lab for LG Electronics Institute of Technology. He then joined the School of Computer Science and Engineering of Konkuk University in Seoul in 2003 as an assistant professor and became a full-time professor in 2012. He has served as the chair of multiple ad hoc groups for developing MPEG-related ISO IEC standards. He's the editor of numerous international standards, and he currently serves as the chair of the standards group presenting to you today. His main research includes smart media systems, image processing, multimedia information, and metadata processing. Professor Yoon, thank you for joining us today, and the floor is yours to get us started.
Thank you very much. Hello, everyone. As introduced, My name is Kyungreo Yoon, and I'm in charge of IEEE Interfacing Cyber and Physical World Working Group. At this webinar, I'm going to explain what we do in this working group and what each part of our working group is about. I'll first introduce IEEE 2888 working group and explain more about each task group. As I and Professor Sang-Kyun Kim are giving this webinar as a team, I'll first present 4 of our projects, and Professor Kim will present the other 2 projects. Please note that the presentation is not in the order of par numbers and is not grouped based on the relevance either. Just for the convenience of the presentation, it is grouped based on the participation level of me and Professor Kim, which means that Professor Kim is more familiar with the last 2 projects of PAR 2888.1 and 2888.5. Okay. First, introduction to the working group. Well, we do not have official scope of the working group, but we have scopes for each individual part. The working group as a whole, we have kind of consensus on the topics that we should deal with. Based on the part we have, I can say that we are providing standardized interface between cyber and physical worlds, and also provide standard or guidelines on building cyber world based on this interface. For this purpose, we first develop interface standard for interfacing cyber and physical world by providing data formats and APIs for the sensors and actuators. Then we provide reference architectures and requirements of applications based on this interface. We also try to develop a visualization interface for cyber and physical world. When I say applications, I mean relevant applications to this standard, and the domain of the relevant applications may include digital farms, digital twins, smart farm, a smart factory, and metaverse, to name a few. So our working group has 6 ongoing parts, and each part is covered by each task group. First 2 parts are about interface for cyber and physical world. First one is about the sensor interface, and the second one is about the actuator interface. Third part is to orchestrate digital synchronization between cyber and physical world. Experts interested in digital twins are mainly participating in this project. Fourth and fifth parts are about a virtual training system. Fourth part is to provide architecture for virtual reality-based disaster response training system through which people can actually move around the physical space to get the training. Fifth part is providing standardized evaluation methods for virtual reality-based training system. We also work on visualization interface, and the 6th part is about the holographic visualization for interfacing cyber and physical worlds. We will give more details on each of these projects. Our working group is an open committee and is based on the individual membership. So any expert who is interested in our work can participate and contribute. If any of the experts who are watching this webinar is interested in our work, you can select your interest in the My Project system or contact me to get involved. There are 3 types of involvement with our working group: observers, non-voting members, and voting members. Currently, we have 18 active voting members. I am chair of this working group. We have 2 co-chairs, Professor Sang-Kyun Kim, who is going to present the latter half of this webinar, is a vice chair of this working group. Mr. Sang-Kwon Jung joined the co-vice chair position last month. He is also secretary and treasurer of our working group. So he's a very important person in our working group. Okay, now I will introduce 4 of our 6 projects. PAR 2888.2, standard for actuator interface for cyber and physical world. This project is like a sibling of PAR 2888.1 in the sense that both of the 2 projects are defining data format and the API for interfacing cyber and physical world. The only difference is that the PAR 2888.1 is for the sensors and PAR 2888.2 is for the actuators. PAR 2888.1 will be explained by Professor Kim later. Now back to PAR 2888.2. This project is approved on December 2020 and has been developed for 2.5 years and now initiating SA ballot this month. The scope of this standard covers vocabulary, requirements, metrics, data formats, and APIs for describing actuator characteristics, setting up the parameters of the actuators, and commanding actuators. How these data formats and APIs for actuators constitutes the interface for cyber and physical world? Because actuators are very important device which can get commands from the cyber world and can affect the physical world. For example, when the wind blows in the cyber world, we can actuate the fan and make the wind blow really in the physical world. This work is chaired by Dr. Taebom Lim of Korean Electronics Technology Institute. To define the data format, we first define a root schema structure using JSON schema, and then define the 16 individual data formats for controlling individual actuators. I have listed all 16 actuators here. Some actuators such as light or heating are to control the environment, and some actuators such as step motor or unmanned moving platform actuators are to control the physical object. And the actuators such as piezo vibration actuators, different kind of actuators, or sprayer actuators, they are more likely used make some kind of effects to the tactile sensor. We also provide data format to describe actuator capability, like the maximum level or maximum intensity that a given actuator can generate, or temperature that a given actuator can operate normally. For the programmers who has to control these actuators, we also define the application programming interface in a format similar to the Java programming language. The advantage of this standard is by enabling transferring a command to a physical world with a standard data format that can be interoperable in different cyber worlds. Also, it offers the capabilities of a description of the capability of an actuator in the standard way to adapt actuator commands in the physical world. This is a simple example of actuator command. In the left box is given the schema of cooling command in JSON schema. And in the right box is an actual example of the cooling command. Here, this command is intended for an actuator that can be identified by the ID of DC-04 and is commanded to generate a cooling effect of -2 degrees in Celsius. This is another example of a step motor actuator. Here, the idea of the designated step motor actuator is DC-21, and this step motor is commanded to rotate 32 steps clockwise at the speed of 10 RPM. This standard provides details on how these attributes and the values shall be interpreted. Next is Part 2888.3 standard on orchestration of digital synchronization between cyber and physical worlds. The scope of this project is to define the vocabulary, requirements, metrics, data formats, and APIs for setting up parameters for the communicating with digital objects to provide the sequences of synchronization and interaction with physical objects. This project is approved on December 2020 and has been developed for 2.5 years and now targeting for the working group letter ballot on October. This task group is chaired by me. In this project, we first define reference architecture for digital synchronization between cyber and physical worlds. This architecture has 4 layers, which are physical world layer, digital twin layer, federation layer, and application layer. We also define the requirements for each layer, and I will explain more in each layer in the coming slides. If you look at this figure, there is a physical robot arm on the left. The motion of this device is captured by sensors, and this captured information is reflected on the graphical model in the virtual world as a digital twin. The digital twin has various models to simulate the operation of the given robot arm, such as a geometry model, structure model, material model, and rule model, as well as process model, so that this simulation can correctly reflect actual movement of this robot arm in the physical world, as well as the process of how this robot is moving. By some simulations of this model in the virtual world, we can decide how this robot should make a move. Then by moving this model in the virtual world, the sequence of commands to move the robot arm is generated and transferred to the robot arm in the physical world, so that the robot in the physical world moves accordingly. This is the basic architecture of the digital synchronization. At the bottom is the physical world layer. At the physical world layer, there are physical twin systems composed of physical entities which are connected to the cyber world by a digital twin, or physical entities which is not connected to the cyber world. Right above the physical world layer, there is a digital twin layer. Digital twin layer has digital twin systems composed of digital entities. Some of those digital entities may be mapped to a physical entity, and some of these digital entities may not have a mapping physical entity. Then there is a federation layer. The federation layer has federation engine, which provides channels for individual digital twin systems to communicate with each other to make a complex service by combining capabilities of multiple digital twin systems. Finally, there is the application layer, which performs user interaction and controlling components underneath this application layer. This standard also includes use case scenarios to provide guide on how this standard can be utilized, or in which applications this standard can be used. Some examples included in this standard are smart farms, smart factories, underground utility tunnels, and smart travel recommendation system. The figure shown in this slide is the case for the underground utility tunnels. Next is the PAR 2888.4, standard on architecture for virtual reality disaster response training system with 6 degrees of freedom. This PAR is also approved on December 2020 and now starting SA ballot process. The scope of this standard is the architecture required to implement a virtual reality system which can simulate possible disaster situations in physical spaces, and users can actually move around with 6 degrees of freedom for training responses to these disasters in virtual reality. This reference architecture includes 3 components, which are: 1, the physical to virtual components that transfers sensor data in the physical space to the virtual world; 2, the virtual to virtual component that conveys the data between virtual world objects; and last, the virtual to physical component that transfers the simulated responses in the virtual world to actuators in the physical world, so that the changes in the virtual world or cyber world can be correctly reflected in the physical world. This is the architecture defined in this standard. Here are physical layer, data handling layer, content layer, and presentation layer. The actual space, as well as the physical components or physical devices such as actuators and sensors, belong to the physical layer. Okay. And data handling layer is composed of data managers and interface to sensors and actuators, so that this data handling layer is handling the data captured through the sensors from the physical layer, or give commands to the actuators in the physical layer. Content layer has scenario manager, interaction manager, situation analyzer, and evaluation manager. The actual scenario or description of actual disaster situation belongs to this layer. So the scenario manager manages the scenario, and the interaction manager creates how this virtual reality application should interact to a certain movement or reactions of the trainee, and the situation analyzer analyzes the situation that the trainee is at, and the trainee is causing by their responses. And the evaluation manager is evaluating the response of the trainee, so that to see whether the trainee is making the proper response to that disaster situation. Finally, the presentation layer with rendering manager, VR display manager, and observation manager. So this presentation manager is responsible for visualizing of what is happening in the virtual space through VR device, as well as flat monitors, so that administrators of this training can watch the whole process and make important decisions when needed. The standard defines minimum of just 8 requirements for the system in terms of how they should operate. Some of the requirements are like this training system shall provide large physical space for the training. This is to provide trainee 6 degrees of freedom. So as the title shows, we are trying to give 6 degrees of freedom to the trainee. So we need large space so that the trainee can actually move around. Another requirement is it shall provide sensor data that captures trainees' full body motion and position. This requirement is to capture the trainees' movement accurately and to capture the context of trainees' response to the disaster situation. So that the response to the trainees' reactions can properly be made. Next three requirements are for immersive VR implementation, such as requirements on audiovisual display, realizing 3D VR space, and VR walkthrough, and 3D accuracy. For the quality of experience, means to interact with the content, and for the effects stimulating human senses are also highly recommended. And the last requirement is because this is a training system, the last requirement saying that it should support the evaluation of the training result, so that we can kind of record and evaluate the trainee's performance. This is the system design for the virtual reality-based disaster response training system. The system has 4 subsystems of content interaction system, sensor system, actuator system, and evaluation system. These 4 subsystems are different from 4 layers shown in the architecture, as each subsystem spans to 2 layers. For example, sensor system, as shown in this figure, sensor system is composed of sensor data manager in data handling layer and physical sensors in physical layer. To make an example of another subsystem, evaluation system is composed of observation manager of presentation layer and the evaluation manager in content layer, as you can see in this figure. This standard also includes the use case and construction guideline of chemical instant response system. I believe that providing such a use case and construction guideline is very helpful for the users of this standard, in the sense that such information can provide a quick start for the users of the system. So if you look at this figure, the figure looks very similar to the one shown in this system design diagram, but the difference is in this system design, this is generalized so that this number of trainees is given as a variable n, and here in the sensors, the personalized sensory equipment number is n. Also, these actuating machines have a variable n, but as this is example, this is in this figure, it is given as a number 6, so that you can see this in this figure. There are 6 trainees participating in this exemplar system, and in this example, the actuator machines are like 2 fans. This is a part of the construction guideline showing when you are building a virtual reality disaster response training system for maximum of simultaneous 6 trainees. This part of the standard gives a guideline for the size of the space and minimum height of the ceiling, and the recommended optical camera sensor location, and so on. So that when you are actually preparing this system, you will see, what is the space that you have to prepare, and how many sensors you have to install, and what is the recommended sensor location, and so on. So this example is for the maximum of 6 players. In other words, if you have this kind of space, it's like a total of 13,000 by 17,000 millimeter space, then you will have some safe distance from the wall, and the play area shall be 10,000 by 14,000 millimeter space. And you should prepare a ceiling height of 2,700 millimeters. And by securing this size of space, you can build a virtual reality disaster response training system for maximum of 6 players or 6 trainees. Okay, now currently the last project is the PAR 2888.6 standard for holographic visualization for interfacing cyber and physical world. This PAR is approved on December 2021 and is the newest project of our working group. It has been just 1.5 years since the approval. Its scope is to define representation of a holographic content to provide interfaces between cyber and physical worlds for objects which may exist either in cyber or physical worlds. This includes holographic printing file format, holographic contents encoding format, holographic representation scheme. We had a slow start on this issue and still preparing its first working draft. This part is led by Professor Hyun-Woo Nam of Dongdok Women's University. Okay, somehow the second page is copy of the first page, and I apologize for that. This figure shows mapping of holographic visualization on the architecture of P2888.3. At the physical world, 3D information acquisition devices, which are kind of sensors, existing to capture information for building holograms, and holographic display or holographic printing devices are actuators to provide holographic images to the users in physical world. In the digital twin layer, these devices are twinned and provides information to the Federation engine so that the data and commands can be communicated and necessary conversion can take place. Then the application layer, the holographic visualization, specific numerical reconstruction, holographic display, holographic printing can be controlled. This standard currently has 3 types of requirements. First one is about holographic printing, such as support of static 3D image, full parallax 3D views, and so on. The second one is about holographic display, such as support of dynamic 3D video, information that should be included, such as the CGH patterns with additional information. And the third one is about numerical reconstruction, such as function to check the hologram representation from digital thing to physical world. This is one use case of holographic visualization. First, we need a holographic generation pipeline to convert digital thing to physical thing with a holographic visualization. So one example of this is the one on the left, by holographic printing based on the recorded Hogel information. Hogel is a mixture of hologram and pixel. The other one on the right is a holographic display, where hologram recorded on single longitudinal mode where the amplitude and phase information is recorded, and by exposing, by using the laser exposure, it can generate or regenerate the images. This slide shows two types of holographic visualization. One on the left is the result of a holographic printing, and the one on the right is the result of a holographic display where multifocus is supported. This is for my part of presentation, and I give my mic to the moderator. Thank you.
Thank you, Professor Yoon, for walking through those 4 parts and very informative presentation there. We have a couple questions. This first question is actually from Brenton. He asks, PAR 2888.4 sounds like a very specialized use case. Why was there a need to develop a standard entirely for virtual reality disaster response training?
Okay. Well, it is correct that this standard is specific to a certain application, but we see there can be many cases of this virtual reality-based training systems, and the one purpose of this standard is we are trying to build a whole system based on our standard. 2888.1 and 2888.2 is providing an interface for the sensors and actuators, and this .4 standard is providing the very nice application built upon those two standards, and it provides a very good guideline to the people who wants to build a virtual reality-based training system based on those sensors and actuators, so that they can easily start building the system. Thank you.
All right. And then I think we have one more question before we go to Professor Kim. I think this ties really perfectly into what he's going to present. But what ties these 6 projects all together into one working group?
Okay. All these projects is based upon the vision of interfacing cyber and physical world. First 2 parts, .1 and .2, are to provide the standard interface for hardwares used for this framework, and .3 is to provide the reference framework for the digital twin-like systems where physical and digital twins can be synchronized. And .4 is providing kind of application-specific reference architecture based on previous standards. And then .5 is designed to provide evaluation system for .4 system. And .6 is intended to provide a visual interface between cyber and physical worlds. So, all together, we are looking at the same vision of building system based on the interfacing cyber and physical world and synchronizing cyber and physical world.
All right, great. Thank you for that explanation. So now we'll move to Professor Sang-Kyun Kim, who received a bachelor's, master's, and PhD in computer science from the University in Iowa in 1991, 1995, and 1997, respectively. From 97 to 2007, he worked on driving simulators and digital content management at Samsung Advanced Institute of Technology. Currently, he is a professor at the Undergraduate School of Convergence Software at Myeongji University in Korea. He is the vice chair of the Standards Working Group and is involved in other standards working groups as well. His research interests include digital content, image, video, and music, analysis and management, fast image search and indexing, color adaptation, 4D media sensors and actuators, VR, Internet of Things, blockchains, and multimedia standardization, to name a few. Professor Kim, welcome, and we look forward to you walking us through the final two developments.
Okay, thank you very much for the introduction, Scott. So I'm continuing on my presentation about the part 2888.1 and part 2888.5. So I'll start with the 288.1. The title is Specification of Sensor Interface for Cyber and Physical World, which is the sibling of the 288.2, which is the actuator interface, just presented by the Professor Yoon. And its proper date was a long time ago, September 5th of 2019. And actually, we are almost end of this part. So this standard defines the vocabulary, requirements, metrics, data formats, and APIs for acquiring information from sensors, and it is enabling the definition of as interfaces between the cyber world and physical world. So the current status is the second round of essay ballot, and I'm chairing this part. So it includes, part 288.1 includes data formats for interfacing sensor data. So it also has the root schema, base root schema for the sensor data, and it has some data formats for individual sensors. So we currently have 31 sensor data, individual sensor data, as follows. Actually, we are starting from the audiovisual sensors like microphone and color camera. And we also have some biosensors like blood and heart rate. And we have about 14 different environment-related sensors like, light, noise, pressure, temperature, and dust, etc. And also we have some location and position-related sensors like GPS, compass, orientation, position, distance, and altitude. And finally, we have many sensors involved in the large space-based electronic system, like button sensor, analog sensor, diode sensor, glove, IMU, rigid body, and band sensors. So also we have some data formats for describing sensor capabilities. It is very useful when you adapt sensor data from the physical world to the cyber world. Actually, cyber world can just adapt the sensor data from the physical world, actual sensor data, with this sensor capability data. So I will show you some example later. And also it has some API for sensors. So this standard provides APIs to exchange the sensor data and its capability between this physical world and cyber world. The sensor data and its capability can be acquired by occurred using these APIs. So the advantage of this standard is to describe sensor data from a physical world with a standard data format that can be interpretable in different cyber worlds. And also it is applying the capabilities of a sensor from a physical world in a standard way to adapt the sensor data in the cyber world. So this is some of the examples. So we just made this schema with the JSON. So JSON schema in this example, this is the example of the temperature sensor. So and its property includes some base attributes of the sensor, so like ID and device ID reference. Sorry. And also it has value and unit. So temperature example, we have syntax and semantics of these elements. So it is written in semantics. And finally, the temperature sensor data can be represented as follows. Like, I mean, in the example, value is 36.5 and unit is Celsius. So it means that, our current temperature sensor data acquired by the temperature device is 36.5 in Celsius. And another one is the sensor capability example. So our temperature sensor can have some sensor capability based attributes. So sensor capability attribute includes something like, maximum, sensor value or minimum sensor value it can acquire. So as you can see in the example, so this temperature device can acquire the temperature from 0 Celsius to 50 degrees Celsius actually. So this is one example. I think this is duplication of the previous one. I apologize for this duplication. Okay, so next one is about the 288.5. The project title is a standard for virtual training system evaluation methods. So it started we started this part on December 8th of 2021. And so this standard defines the evaluation methods for virtual training systems. So both subjective as well as objective evaluation methods are defined. So together with evaluation criteria, evaluation questionnaires, and evaluation metrics that can be used to evaluate the effectiveness, efficiency, and satisfaction of virtual training system. This standard also defines the experimental methods for evaluation, including setting the experiment's environment, selecting test subjects, configuring the test subject group, designing the experiment, and the experimental procedures as well. So we just started this week actually. We working group led ballot. So I'm chairing this part as well. So again, the purpose of this part is to standardize the guideline for evaluation of VR training systems, which can be applied in various industrial areas like digital twin, smart applications, and metaverse. And this standard defines the evaluation framework for virtual training systems. So actually, this evaluation framework includes the plan, design, data, and test, finally, and analysis. So I will talk to you about that one by one in detail. So the first one is the plan. So we have 4 items included in this plan. So the 4 items, first of all, the first one is the purpose of the evaluation, and the goal of the VR training system should be defined clearly. And the characteristics of the VR training system should be defined as well. And then finally, hardware of the VR training system should be defined. And then finally, the actual consumer of this training system should be defined clearly. The next one is the design step. So the design step determines the experimental design for the evaluation of the VR training. So we can include the IRA for the human test. And also we have some evaluation indicators like for the effectiveness, we can just measure the immersion level and task performance and degree of user engagement. And then the usability indicator can include the learnability of the system and also the visibility of the system, like GUI. And then finally, the acceptability includes the tendency about the user can willing to purchase this system or purchase recommend this system to others like that. So these three indicators are can be measured with our test procedure. And another one is about the experimental design. So we can just design the experiment for the system two ways. In two ways. The first one is the between graph design, and within the another one is the within graph design. So next step is about the data. Actually, we have two kinds of data: the quantitative data and qualitative data. So as you well know, the quantitative data should be defined with the numerical value that can be drawn from participant, test subjects. So it is the result of the questionnaires can be marked with the 7 Likert method like that. And another one is from the sensor, physiological sensor. From EEG, PPG, or eye tracking, we can just extract some kind of actual human biosensor sensor data, and then we can just measure some result. And another one is the qualitative data. It is non-numerical data that can be drawn. They can draw detailed information from participants or test subjects. So it is including in-depth interview, focus group interview, and observational notes by the observer. Okay, and the main thing is about the test. Actually, we can start with the pilot test. It is a small-scale version of the main test to assess feasibility of the evaluation design and find out any problems before the main test. And then main test is composing of 5 steps actually. So we start with the introduction about the system, and then we can survey some questions before the actual test. That is the pre-survey stage. And the next stage is about the baseline measurement. So you can acquire some information from human signal, something like that. And so baseline measurement is included in here. And the next one is the VR training system test. Actually, this is the actual test for the VR training system. So training system, experiencing VR training system, and then some physiological data is obtained during this period. And then after all the VR training system testing, we perform the post-survey with the questionnaires, and then we can just conduct the interview. And the last part is the analysis part. So we have 2 different parts, comparative evaluation. So we can just compare data from different setting or different conditions to objectively present the evaluation widgets, or we can have some single evaluation. So we can conduct gain valuable insight from participants or test subjects without comparing to other conditions. So I think this is the end of my presentation. So maybe next slide can be presented by Professor Yoon. So I will hand over this presentation to moderator. Thank you.
All right. Awesome. Thank you, Professor Kim. That was also very informative. Before we have Professor Yoon go over the slide, I think there's one question that came in regarding 2888.5. Has the process presented been applied or tested before the actual VR training?
Yes, actually, this evaluation method and procedure was tested before the standardization. Actually, it was applied for the VR training system for Army, policemen, and firefighter. Actually, we had this type of VR training system, and it was this type of the procedure presented in the 288.5 was tested before standardization, and that's my answer. Thank you.
All right, great. Let's bring Professor Yoon back on for a Q&A, but Professor, you just want to walk through these dates and what these future sessions are real quick?
Yes. Before I go to these future sessions, I was informed that the 2888.5 process has been tested for more than 20 virtual reality training systems. And regarding these future sessions, we have one more session coming this year, which will be held at the Best Western Plus Hotel in Jeonju, Korea. And next year, 2024, we will have 3 meetings, one in February, July, and October. In February, we plan to meet at Sydney, Australia. In July, we'll meet at Budapest, Hungary. And October, we'll meet at Gyeonggi-do, Korea. And 2025, we are planning to meet in February at Barcelona, Spain. On July at Sao Paulo, Brazil. And on October at the Ocean Hotel of Jeollanam-do, Korea. That's far south of Korea. Thank you. If you are interested in participating in any one of those meetings, please let us know. Thank you.
All right, great. And then we have some questions that came in. Where this is regarding 2888.1. Is there somewhere where they can download the data format?
Well, actually, yeah, this is almost end of this. A ballot, IEEE ballot. So maybe, I don't know. Maybe you can buy it after standardization.
Yeah,
I don't know.
I think I can answer that.
Yes.
Actually, the draft itself is internal document, so you'll be able to download it once you participate in the essay ballot, or you'll be able to make an access to the document as soon as the standardization process is finished and the document is published. I don't think it will be far away from now. It will be done in like 3 or 4 months from now on. Thank you.
Okay, and then what we'll do is, since they mentioned, the two professors mentioned a couple of times the ways to get involved, I think we've forgotten to include that information on the slide. So I'll get a link or an email from them, and we'll put that in the email everyone receives tomorrow. Our next question is from George. This is regarding .2. So for 2888.2 for actuators seems to include simple actuators like step motor as well as control systems like the refrigerator. Does .4 does the
Yeah.
does the .4 spec
Mm-hmm.
scope include control systems?
I think there's a little bit of misunderstanding in that too. First, it has actuators, like simple actuators like step motor, but we do not have a control system like the refrigerator. I said something like cooling, but it's not like the refrigerator. It's more like an air conditioner, or yeah, it can be a refrigerator, but the command itself is quite simple. You designated the temperature, intended temperature, even for the refrigerator. So it's kind of straightforward, even though you call it control systems. How you control the temperature depends on the system itself. It's not within the scope of this interface. And the question about does the 2888.4 spec scope include control systems? Not really. I guess not really. This .4 spec specifically has scope within this virtual reality based training system. So it's, I believe, different from this control system that George is mentioning. Thank you.
All right. I think we're at the top of the hour, so we'll have. I think we have three sort of quick questions. You mentioned the meetings where there's a question out there. Is there a virtual component to these meetings, or are they all in person?
Meaning?
The future sessions, like in
Yeah.
Korea, is there a virtual component, or is it all in person work?
Oh, they are intended for all in person.
They're all in person. Okay.
Yes.
Actually, I think this is a really good final question. It seems that most of the projects are at the stage of finishing specification for their standard. What's next for the working group, and are there any projects plans to start new standards and new projects in the near future?
Okay, the .6 holographic visualization is still in the middle, very early stage of developing standard. And recently, we have received a proposal for a new part, which would be developing a reference software and conformance testing for .1 and .2, so that we can actually see and check the compatibility of the system based on .1 and .2. And we are also open to new proposals that would facilitate the interface between cyber and physical world, as well as the synchronized and as well as the proposals based on the idea of synchronizing cyber and physical world. Thank you.
All right, great. Well, I think that brings us to the end of today's webinar. I would like to thank Professor Yoon and Professor Kim for joining us today and sharing everything that is going on in the Interface, Cyber, and Physical World Working Group. I also like to thank all of you for attending today's webinar. Just a quick programming note, the IEEE Computer Sci is hosting 2 additional webinars in the near future. The next one is actually about 48 hours from now, so Thursday, 11 a.m. Eastern. That webinar is from our Build Your Career webinar series, very focused on soft skills that are vital to everyone in their office setting. Thursday's topic is titled Leading Positive Change. The next webinar from this standard series is on August 23rd, which will be Quantum Computing Energetic Performance from NISQ to FTQC. Once again, I want to thank all of you for attending, our 2 speakers, Professor Yoon and Professor Kim, for joining us today. Thank you and have a great rest of your day.
Thank you very much.
Okay, thank you.
Mr.
Thank you very
Levin.
much.
Thank you, Professor Kim.
Thank you. Thank you.